Anthropic keeps telling the world that AI is coming for software engineers. And yet, if you actually try to become a software engineer at Anthropic, you'll face one of the most punishing hiring processes in the entire industry. For years, the big tech giants owned that reputation. You wanted in, you trained for months. Algorithmic challenges, system design marathons, behavioral rounds engineered to break your composure. It became such a cultural moment that entire companies were built just to coach people through it. Well, based on a detailed breakdown someone posted on Reddit recently, Anthropic studied that playbook, mastered it, and then added extra levels just to be safe. So today we're walking through exactly what their technical interview looks like. 5 rounds, 3 weeks, and enough concepts to make most developers quietly reconsider their career choices. Even if you never apply there, the problems are worth knowing. This is the vocabulary of engineers building the infrastructure that runs modern AI. Round 1. Online assessment. The first round is a timed online assessment. 2 problems, 90 minutes. The goal is simple. Filter out anyone who can explain software concepts fluently, but freezes the moment they actually have to implement one. So, naturally, this is where most of us would be eliminated. The first problem was implementing an LRU cache. Least recently used is one of the most common cache eviction strategies in software. The concept is clean. A cache has fixed capacity, so when it fills up and something new needs to come in, something old has to go. LRU removes whichever item has gone the longest without being touched. Simple in theory, the kind of thing that feels obvious right up until you're staring at a blank editor with a timer running. The naive approach is to store everything in a regular map and scan through it on every axis to find the stale entry. That works technically, but it completely defeats the purpose of a cache. You've turned your constant time lookup into a linear scan. Your optimization is now your bottleneck. You built a fast lane and then put a toll booth in the middle of it. The real solution combines a hash map with a doubly linked list. The hash map gives you constant time access to any entry by key. The doubly linked list maintains usage order. Each node stores its value plus pointers to both neighbors, so you can remove any node from the middle in O1 time. When a key is accessed, its node moves to the head. When the cache is full, you drop whatever's at the tail, which sounds elegant until you try implementing it cleanly under a timer while someone watches you type. The second problem was a task management system where tasks had priorities, worker assignments, and dependencies on other tasks. Cancel one task, and everything downstream had to cascade, and cancel 2. The moment you hear depends on, you should be thinking graphs. If task B depends on task A, then A has to finish before B can run. The right model is a directed acyclic graph, a DAG, with topological sort to determine execution order, a priority queue to pick the best eligible task at each step, and a downstream traversal to propagate cancellations. 3 distinct algorithmic concepts, combined under time pressure in round 1. That's the warm-up. Round 2 moves into live coding. Now you're not just solving isolated problems. You're building something that behaves like real software, edge cases included. The task was to implement a web crawler. Start at a given URL, crawl outward using breadth, first search up to a certain depth, extract links, deduplicate them, and build a sitemap. All while rate limiting yourself so you don't accidentally take down someone's server. The core is a queue initialized with the starting URL. For each URL you pull off, you fetch the page, extract outgoing links, normalize them, and in-queue anything you haven't visited yet. A visited set is non-negotiable. Without it, you loop forever. The web is a graph full of cycles, and even simple sites have circular navigation links that will spin your crawler indefinitely. One badly handled loop, and your program quietly hammers a hobby blog at 2 a.m. until their hosting provider sends them an angry email. Rate limiting brings concurrency into the picture. You control how many fetches run at once using a semaphore, a counter initialized to your max concurrency, say 5. Before launching a request, a worker decrements the counter. If it's already at 0, it waits. Once a fetch finishes, the counter goes back up. It's one of the cleaner concurrency primitives, and the fact that it appears in round 2 tells you exactly where this interview is heading. Round 3. System design. The system design round is where the nature of the interview changes entirely. You're no longer being tested on whether you can code, you're being tested on whether you think like an infrastructure engineer. The task? Design an inference API for serving large language models. This is literally what Anthropic builds. The interviewer isn't working from a rubric, they're comparing your thinking against decisions they've actually made in production. There is no hiding behind a textbook answer here. The first challenge is that requests are completely non-uniform. One user sends a 3-sentence prompt and wants a quick reply. Another sends a 10,000 token document and wants detailed analysis. Entirely different runtimes, entirely different GPU memory requirements. Treat them the same way and your system falls apart fast. GPU utilization is the real constraint. Running one request at a time wastes most of the GPU's capacity, so inference servers batch requests, grouping them so the GPU processes several in parallel. But batching strategy matters. Mix very short and very long requests in the same batch, and the short ones sit idle while the GPU grinds through the longest one. Everyone waits for the slowest person at the table. Good batching groups requests with similar expected lengths, which requires estimating workload before execution even begins. Then there's KV cache management. During generation, language models cache intermediate attention states so they don't recompute earlier tokens on every step. That's what makes generation fast, but that cache lives in GPU memory and grows with every token produced. With dozens of concurrent requests, each with its own expanding cache, memory pressure becomes a genuine operational problem you can't ignore. Streaming adds one more layer. Most modern inference systems don't wait until generation is complete before responding. They stream tokens to the client as they're produced. Each request becomes a long-lived, continuously active connection. Now you're managing back pressure, client disconnects, and partial results at scale. One slow client can quietly hold a connection open for 30 seconds while your server keeps allocating resources to it. This is senior infrastructure engineering territory, and this is round 3 of 5. Round 4, second coding. Round 4 returns to code, but these problems feel less like interview prep and more like something you'd actually encounter building real systems. The task involved processing the output of a sampling profiler and reconstructing a timeline of function execution. Sampling profilers work differently from the kind that instrument your code. Instead of recording every function entry and exit, a sampling profiler periodically interrupts the running program and captures a snapshot of the current call stack. Lightweight, non-invasive, but the trade-off is you only get snapshots, not events. You don't know when functions started or ended. You only know what was on the stack at each sample point. The full execution timeline is buried inside a sequence of frozen moments. The reconstruction approach is to diff consecutive stacks. Compare two adjacent samples from the root downward until they diverge. Everything in the previous stack below that point has exited. Everything in the new stack below that point has started. Process all the diffs in sequence and you rebuild the complete timeline, turning silent snapshots into a readable story of what the program actually did. It's an unusual problem. You won't find it on any LeetCode list. There's no flashcard for it, which is exactly why it's here. By round 4, they're not testing whether you studied, they're testing whether you can reason. Round 5, behavioral. The final round was behavioral. Standard competency and culture fit questions. Nothing technically remarkable. And honestly, if you've made it through the first 4 rounds, the behavioral conversation is almost a relief. What's worth sitting with after all of this isn't just how hard the process is, it's what the problems reveal about the moment we're in. graphs, caching, concurrency, KV memory management, profiler reconstruction. These aren't trivia questions pulled from a prep sheet. These are the actual building blocks of the infrastructure running every major AI system right now. Anthropic is, famously, the company arguing that AI is solving software engineering, but their bar for the engineers they actually hire suggests they know exactly how much hard engineering still sits underneath that claim. Let me know in the comments which round you'd feel most confident walking into, and which one would end your run. See you next time.